Hello everyone, welcome to the electromagnetic fields video series. In this new video series, we are going to discuss about the topics of unit 3, which is magnetostatics. In the previous video series, we have covered the basics of electromagnetics and then we recalled the topics in electrostatics, and now we are moving on to unit 3, magnetostatics. So in this video, we are going to discuss about an important law which governs magnetostatics, which is the Ampere's law. So let's get into the video. So before diving deep into the Ampere's law, let's recall the concepts that are being inculcated in magnetostatics. So there are three fundamental laws that governs magnetostatics, which are the Lorentz law of force, Biot-Savart's law, and Ampere's circuital law. So in this video, we are going to discuss in detail about Ampere's circuital law, which is Ampere's law. So these are the agenda that we are going to follow for this particular video. So we are going to discuss in detail about Ampere's law in a DT based approach. So we are going to first empathize the Ampere's law, what is the real need for Ampere's law, and then we are going to define the problem statement, then visualize how these fields comes about, and then we are going to prototype this Ampere's law through a long straight wire, and then we are going to test and validate to confirm Ampere's law in practice, and then we'll be seeing some real world applications, and then finally we'll have a summary of all those discussions. So first, what is the need for Ampere's law? As we know that whenever a power transmission line run close to the residential zones, we must estimate magnetic field levels for safety and designs. In general, we are very much aware that whenever a current is flowing through a conductor, an invisible magnetic field will be produced around the conductor. So, what is the magnetic field around a power cable or coil? What is the reason or how much this magnetic field will be? So, for this also, consider another example where we have to design a current sensor or a magnetic shielding around a cable. In order to do so, then we need to have a knowledge about what is that magnetic field around the power cable, how much it will be, and how it is produced. So here the problem statement is that to compute the magnetic field around a current carrying conductor using a simple yet powerful method. We know there are different laws as we mentioned earlier, but certain are somehow complicated. So we are now making it in simple with a help of this Ampere's law. Now let's visualize this field, how it comes about. For example, in a closed current loop, we use the right hand rule, wherein which the thumb represents the current and the fingers curl directions the magnetic field flux density. For example, in a USB charging cable, the current in that wire produces a tiny magnetic field around it. So now, even there are different shapes of conductors or coil, but how can we calculate this magnetic field in that coil or conductor irrespective of its shape? Now, let's get into the topic. By Ampere's law, we know that B dot dl is equal to I. So Ampere's law states that the magnetic flux density in around a conductor will be directly proportional to the amount of current flowing through it. That is what Ampere's law is all about. So here B is equal to mu naught I. So integral B dot dl is equal to mu naught I, where mu naught is the permeability. Suppose we are considering a long straight wire, wherein which a 50 amps of current is flowing at a point 0.1 meter away. Now, for this case, the formula will be B is equal to mu naught I by 2 pi r. So we know the current value, which is 50, and we know how much distance it is away from the cable, which is r is equal to 0.1 meter. Therefore, by substituting all these values in the equation, we can easily estimate the amount of flux density that is being produced with the help of the current around the conductor. So using this in designing spacing between current carrying wires, we can find the interference of these EMFs, thereby we can minimize it. Also, we can use another prototype wherein which we can use a solenoid. So we have already looked for a long straight conductor. Now we can analyze for a solenoid. For a solenoid, the flux density through the solenoid will be B is equal to mu naught Ni, where N represents the number of turns and I is the currents. So through these formulas which are being derived from Ampere's law, we can easily find the magnetic field intensity or the flux density for any sort of conductors. For solenoid, you can think that the number of turns is directly proportional to the flux density. So therefore, if we increase the number of turns or length or the conductor size, will that affect the flux density? Yes, definitely it has. That is the basic principle of that is the basic principle that we are using for electromagnets. If we consider another example of toroid, for which the flux density equation is B is equal to mu naught Ni by 2 pi r. Since for a long straight conductor there will be no number of turns, therefore B is equal to mu naught I by 2 pi r. But for toroid, the equation is very similar, but it includes N, which says that the flux density is directly proportional to the number of turns. So if we want to produce an external stray field, then these kind of toroids are very much useful, and this is the basic principle of an inductor. So therefore, inductors in switching power supplies, where we want to control field with minimal outside interference, these Ampere's law is useful in finding how much magnetic field can be produced from any sort of conductor irrespective of its shapes. Now, how can we change this current, thereby producing the magnetic field with respect to time? So for a time varying magnetic field, the Ampere's law can be reformulated as integral B dot dl is equal to mu naught into current enclosed plus epsilon naught d phi by dt, which is the electric field part. So therefore, for producing a magnetic field, the electric current plays a vital role. So the electric flux plays a vital role. That is why for time varying fields, this electrical field part, electrostatic part, is also being added to this Ampere's law, which is called as the modified Ampere's law or the Ampere-Maxwell's law, where epsilon d phi by dt is called the displacement current. Now we are going to test and validate to confirm Ampere's law in practice. We are going to compare Biot-Savart law and Ampere's law. We know that Biot-Savart law is, somehow for a differential current element, but Ampere's law is for a total volume. So if you want to, but both yield the same answers, but for complex cases, it is very easy to inculcate or apply Ampere's law rather than using Biot-Savart law. So we can easily confirm this or validate this by using an experimental setup, wherein which we can use Hall effect sensors to measure the magnetic flux density, and we can use magnetic compass for deflections and transformer core and coil assemblies. So these are the real world applications wherein which we can find the Ampere's law role in designing. For transformer design, for electric motor designs, wireless chargers, magnetic levitation trains, and cable routing in high voltage systems, even more. So these are few cases wherein which we use Ampere's law in determining the magnetic field. So for transformers, we estimate the leakage field using Ampere's law. For electric motors, we estimate the field around the windings. And for magnetic levitations, we use this Ampere's law to find the force field, magnetic force between the two coils. And for cables, we ensure electromagnetic compatibility with the help of Ampere's law only. So using this Ampere's law, we can easily compute the magnetic field density for a complex cases. And also it has no symmetrical limitations, or irrespective of size or shape we can apply Ampere's law for any sort of fields. And also we have modified Ampere's law to apply for dynamic fields also. So compared to Biot-Savart law, Ampere's law is very easy to apply for complex cases. So these are the reference that I've been used to share with you through this discussions. So if you have any clarifications regarding that, you can comment below, or you can go and check these links for your preparations. So I hope in this video we have clearly discussed about the Ampere's law, and also we have seen the major difference between Biot-Savart law and Ampere's laws also. So in the next video, we will see the rest of the laws that are governing magnetostatics. Thank you. Thanks for spending your time in listening to this video. Thanks for listening.